next is Emre Yolcu. Hi, Emre, could you please share your slides?
Yep.
Am I pronouncing your first name correctly?
Yeah.
Thank you. So Emre is a PhD student at Carnegie Mellon, and he is interested in all things satisfiability, but in particular applying satisfiability to math. And today he's going to talk about applications of SAT solvers to this extraordinarily hard problem called the Collatz conjecture. Emre, we can't see your, at least I cannot see your screen.
Can you see it now?
Yeah, now I can see.
Just a second. So maybe in presentation mode it's not working. Can you see it now?
Yes, I can see it.
Good.
Yes. So please go ahead and give it up. Thank you so much.
All right. Thank you for the invitation. I'm very excited to be talking about this. So as the title suggests, this is our attempt at tackling the Collatz conjecture via automated methods that are based on string rewriting systems, specifically their termination, a method for proving termination called matrix interpretations, which uses satisfiability solvers in the process. So this is joint work with Scott Aronson and Marijn Hoyle. Yeah, so this doesn't require much introduction, but as you well know, several open problems in mathematics were solved using computer-assisted approaches or purely computer reliant methods. So most of these instances were solving a finite but really large search problem in general. For instance, when you use satisfiability to refute a formula, you're solving a finite search problem, or when you're finding some counterexample to a statement, you're again solving a finite search problem. It's rarer that one gets to solve instances of problems that are in general undecidable. So termination is one such instance, and there are beautiful techniques developed to prove termination of string rewriting automatically. And in this work, in a single sentence, we are going to look at variants of the Collatz conjecture and see what we can achieve using the techniques that have been developed for automatically proving termination of string rewriting. And more specifically, we will design a rewriting system that is terminating if and only if the Collatz conjecture holds. And spoiler alert, we will fail to prove it to be terminating, but we will look at some weakenings of the problem and see what we can achieve, and I will show some partial results. So a draft of this paper is available at this link in case you want to check it out. In about 10 days, we will also put a full version on archive, and this work will appear at CADE this year. So I'm assuming that not everybody in the audience is familiar with rewriting, so I will introduce it quickly via examples. I won't go into too much technical detail, but I just want to give you the intuition and also show you the notation for that we will use. So in string rewriting, it is best thought of as a non-deterministic model of computation that works with strings. So we have an alphabet of symbols. We have rewrite rules denoted L to R, which map some string to another string. So this is the replacements that we can do in parts of the string. And the collection of rewrite rules constitutes a rewriting system. So formally, this is a relation over strings over this alphabet. And then we also have this rewrite relation, which is induced by the rewriting system. And this is the relation describing the strings for which you can write one into another using some application of a rewrite rule in the string, in the system. So here is an example. We have a single rule system R with the rule A, B, B, A. And generally, I won't specify the alphabet. We'll just take it implicitly to be the all the symbols occurring in the rewriting system. So here's a sample rewrite sequence. So the sequence of applications of this rewrite relation, we will call a rewrite sequence. So here I'm showing the part of the string that we are applying the rule to. We have a single rule in this case. So we have this string. We can pick some part of it that matches this pattern AB and then rewrite it into BA. So we rewrite it, obtaining this string, and then we repeat the same process. Continuing until no rule can be applied, and which happens when all the B's are pushed to the left of the string and all the A's are pushed to the right of the string. So the interesting property of the rewriting systems that we will look at is termination. So a system is said to be terminating if there is no infinite chain of rule applications. So where each of these X's are strings over the alphabet that we have. So note that this is a universally quantified statement over all strings and all rewrite sequences. So we are not prescribing some strategy for applying the rewrite rules or prescribing some starting language. A system is terminating if for all strings and all possible rewrite sequences, there is no infinite chain. So the rewriting sequence has to come to an end. Again, here are some simple examples. The last two are not so simple. So this is the one that we saw. So this is easily seen to be terminating because it moves A's to the right of the string and then B's to the left of the string and stops when all the B's are accumulated on the left and A's are accumulated on the right. So these two are like very trivial examples of non-terminating and terminating systems. So this is non-terminating because you can keep increasing the length of the string by rewriting a single A anywhere in the string into two A's. And this is like doing the inverse. So you keep reducing the length of the string until a single A remains. So you can't keep rewriting indefinitely. So this one has a loop, again, a trivial loop. So you can figure out some A and then rewrite it into B and then rewrite it back into A again, obtaining a loop. So this one is a peculiar one. So it's very nicely symmetric and small, but it's not at all obvious whether this is terminating or not. And it is terminating, although this wasn't known for a long while. So this one is also kind of small alphabet as well, just two rules, but it's open whether this is terminating or not. So nobody knows right now. So for proving termination, several techniques have been developed, and the good reference for this is the Baader and Nipkow textbook. So we can characterize termination as the existence of some well-founded order over strings, such that for all strings, if you can rewrite it into another string using some rule application, then according to this order, the string should decrease. And since the order is well-founded, you cannot keep rewriting ad infinitum. So you cannot have infinite chains of decreasing strings. So this shows that the system is terminating. But this is again it's a condition over infinitely many strings that you have to check. So it's not very amenable to automation. So instead, the following approach is used. So I'm describing it a bit abstractly here. So you can translate any given symbol in your alphabet into an element. So this brackets means that you're translating it into another element in some domain. So this is the translation. And this domain is going to be already equipped with a well-founded order. So we don't want to explicitly figure out an order on strings. Instead, we will use another domain. And then we want to show that for all the rules, if you extend this translation of symbols into strings in some manner, and furthermore, if under this translation, this order holds this order relation holds for all the rules, then your system is terminating. So this is here I've compressed the conclusions of several theorems while omitting some details. but this is like the general idea, and this is called the interpretation method. So now I'll show you a very trivial example. So consider this system again. We can interpret this, there's a single symbol. We can interpret it as just one. And the domain that we are translating this to is the natural numbers. And to strings, we extend this additively. By that, I mean the interpretation of a string is the sum of the interpretations of the symbols that it has. So then you see that you have this decrease by rewriting the string according to this interpretation. And this suffices to show that the rewriting system T is terminating. Now with this sudden shift of gears, we can also translate the symbols into functions more generally than numbers. And for instance, for this system, you may observe that this additive translation doesn't really work because AB is going to have the same interpretation as BA under whatever interpretation you have, as long as you're extending to strings additively. So instead, you may consider functions and extend to strings in a compositional way. And by that, I mean the interpretation of AB is the function that is the composition of A and B. If you can ensure that this function dominates this function, the other function, then this also serves as an interpretation method proof. And this lends itself very well to automation for certain templates of these functions that we can pick. So one very effective method that was invented by Hofbauer and Waldmann in 2006 is to translate these into affine functions over the natural numbers, vectors of natural numbers for some fixed D that you pick. And this is also extended to strings compositionally. And this means that if you compose these interpretations for the symbols to get the interpretation of a string, you get another affine function. So everything is interpreted in terms of affine functions. And then you equip it with some order that is defined as follows. So a vector is greater than another vector according to this order if it is greater than or equal to component-wise, and furthermore, if it is strictly greater in the first element. So it turns out that this satisfies all the technical requirements that you have. And under this, you get the ability to search for interpretations of this kind automatically. Specifically, we look for interpretations that satisfy this relation. So L and R are the left-hand side and the right-hand side of some rule. And these matrices and these vectors are the interpretations that you have for these under some fixed interpretation of the strings. If you can check that this holds for all X, then you get you have an interpretation, you have a termination proof. And the very successful idea here has been to encode all of the resulting constraints from this as a set instance. So in the end, you have a formula that is satisfiable if an appropriate interpretation exists. So you can use a SAT solver to see if it exists, and if you can find one, then that proves that the system that you have is terminating. Now I'll explain it a bit more concretely with an example. So recall this one. So this was well known for not having a proof for a long while, not just automatically, but in nobody could prove in any way whether this was terminating. And the first ever proof of this was found, proof of termination of this system was found automatically using matrix interpretations. And just compactly, it's these. So under these interpretations, all of the rules have the decreasing interpretations, as I showed here. So with respect to this order. And here I'm showing you the resulting affine functions from composing the affine functions for the symbols. And here we are performing a check that is for, that has to hold for all vectors. So you can do it decidably by comparing, since you have this order, you can do it decidably by comparing the matrices and the vectors element-wise. And turns out that this order holds if element-wise the matrices are greater than or equal to on the left-hand side compared to the right-hand side, and the same holds for the vectors. And furthermore, you require that the first element of the vector decrease strictly. So this constitutes a proof that this system is terminating. Again, there are a few more constraints that I'm omitting, but I'm just trying to give you the intuition. So moving on, although this needs maybe no introduction, let me just fix notation. So this is the Collatz function. If you have a even integer, you divide it by 2. If you have an odd integer, you multiply it by 3, add 1, and then it will become odd, so even, so you divide it by 2. So the Collatz conjecture, the notorious conjecture, says that for all positive integers, iterated application of this function reaches 1, and then keeps going as 1, 2, 1, 2, and is stuck in that cycle. So this has been checked up to, as of this year, 2 to the 68, that all of the trajectories do indeed reach 1. Although, we are nowhere near finding a proof of this. And so we will design a rewriting system that's terminating if and only if this conjecture holds. And such a rewriting system actually exists and was invented by Hans Zantema in 2005. I won't explain it in too much detail, but I just wanted to show you. And you can view this as encoding the computation of a Turing machine with elastic tapes. That is, you have, let's say, a unary representation of a number on a tape. And then you can, by applying these rules, contract, or by applying this rule, expand the tapes of the strings, of the Turing machine. So the symbols are suggestively named. So ones indicate the ones in the unary representation. H indicates the head of the Turing machine, and along with the state. So it's halving a number at this state. So these diamonds are the blank symbols on the tape. This shift is the shift operator, again, encodes the position of the head on the tape. And this moves the head leftward without changing the value of the string. And this T serves as what the head does while it's tripling the number. So Zantema showed that the above system is terminating if and only if the Collatz conjecture holds. So the forward direction of this implication is kind of easy to see once you become familiar with this system. Specifically, you have the following rewrites possible. So if you have the unary representation of 2n on the tape and the head is on the left of the string, then there exists a rewrite sequence that allows you to get to n. And if you have the representation of 2n plus 1, then you get to the unary representation of applying the Collatz map on 2n plus 1, which is 3n plus 2. So then if this is terminating indeed for all rewriting sequences, then it is terminating for these sequences as well, which shows you that the corresponding Collatz trajectories are terminating. But this system using the unary representations, we argue, is not very amenable to automated approaches. Specifically, if you consider a simplification of this system that is like trivially terminating, so you may adapt this to compute the function that divides by 2 and multiplies by 3, as long as the result is an integer, and then stops when the number is not divisible by 2 anymore. So that leads to a 4-rule system for which termination is trivial to see, but no automated method has ever succeeded. So we will design an alternative system for which that problem and even some more difficult problems that are still easier than the Collatz conjecture become solvable. And it relies on a few simple observations. So we will work with a mixed binary-ternary representation of the numbers instead of a unary representation. So we observe that we can view binary representations of the numbers as compositions of the functions that correspond to the true bits and the false bits. So the false bit multiplies a number by 2. true bit multiplies by 2 and adds 1. And also we have like a constant function denoting 1. So as an example, so we can write 12 in binary in this manner. So this is the most significant bit. And then you can translate that to a function view by, I guess, an application of Horner's rule in this manner. So you revert all of the symbols. So you get 0, 0, 1, 1. You replace zeros by false, ones by true, and you replace the rightmost one by this constant. So then you can check that evaluating this gives 1, and then evaluating this gives 3, and then evaluating this gives 6, and evaluating this gives 12. So why are we doing this? Well, because this has some nice properties regarding the Collatz function. So specifically, division by 2 in binary corresponds to just erasing one of the least significant bit. So in the function view, it corresponds to just deleting this f. And if you apply that to 12, you get 6, which has this representation, and then you can repeat it again, getting 3. So now we have an odd number. Now, the Collatz function involves dividing by 2, but also multiplying by 3 and adding 1, which is not so easy to express using just binary. But if we also had a function, let's say, of this kind, then we could write, let's say, 3x plus 1, which gives us 10, in this manner by composing additionally with this h. So you can iterate on this idea and end up with a binary-ternary system, mixed binary-ternary system. So the symbol f and t correspond to the 0 and 1, so the binary bits. The 0, 1, 2 functions correspond to the ternary digits 0, 1, 2. And these functions serve as the markers, the beginning and the end of string markers that we will use. Again, an example. So we can, for instance, write 19 in this way, in the mixed representation. So this is the string view, and you may view this 0 as a ternary digit, this false, this f as a binary digit, and so on. And in the function view, it corresponds to this composition. Now we would like to apply, let's say, the Collatz function to this representation. But unfortunately, from this, by just looking at this representation, we can only say that this is a number of the form 3x plus 1. So we are unable to recognize its parity immediately. If this was a binary digit, then we would be able to recognize its parity immediately. So we will rewrite parts of the string in such a way that its value doesn't change, but in its representation, this function is a binary function, or a function that corresponds to a binary digit. So specifically, we will rewrite, we will swap the basis of these adjacent positions. So we have 1 fx evaluate to 3x plus 1. You can rewrite it by moving a binary digit outside and moving a ternary digit inside. But then, while doing so, we also want to ensure that we don't change the value of the string. So these functions are picked accordingly. This shows that we could replace this 1f with 0t to arrive at this number, still representing 19 with a single modification. Now we are able to recognize its parity, so we can apply the Collatz map at the rightmost end. Because this representation says that this is a number of the form 2x plus 1 for some x. So mapping that to the value that the Collatz function would map it to would entail replacing this part of the number with these two symbols. So specifically, you had a number of the form 2x plus 1. you would like to make it a number of the form 3x plus 2 for the same x. So you can do that by deleting this, and instead of its place, putting 2, which we interpret as 3x plus 2. So in this way, you simulate the Collatz function's application on the string in a single step, as long as the rightmost end is a binary digit. So in this manner, you can work out all of the rules that you need to have and end up with this system, whose termination is equivalent to the Collatz conjecture, as in the previous case, but this is using a different representation. So these 9 rules that you see on the right are the auxiliary rules that serve to move binary digits towards the right end of the number so that we can apply the Collatz map in a single rewrite step. These 2 rules are just applying the Collatz rule. So if it's a number of the form 2x, you rewrite it into a number of the form x. And this we have already seen. So in order to have some practice with it, this is an example sequence and how this would work. So suppose you have this representation of 12. So again, this doesn't end with a binary digit. So we would like to rewrite it. And we rewrite it according to this rule, f0 into 0f, obtaining a representation that ends with a binary digit. Now we can freely apply the Collatz map. So we use this rule to rewrite it into this string, which gives us 6. And in this manner, we continue until we derive 1, which is represented uniquely by this string, which we cannot rewrite further. So this rewriting sequence witnesses the convergence of this Collatz trajectory. So this system is in some ways better than the unary system because it lends itself better to automation. But we, of course, failed to solve the Collatz conjecture with this. So what one does when failing to solve the problem is look at partial problems or like easier instances of the problem. So one non-trivial test that we subject this system to is a variant of the Collatz function that Farkas studied in 2005. So this is known to be terminating. And you obtain this variant by introducing an additional case to the Collatz map. So if the number is 1 modulo 3, then you subtract 1 and then divide by 3. Otherwise, you apply the original Collatz map. So Farkas showed that you can prove inductively via case analysis that this function is convergent. And using the same idea as before, we can translate all of these rules. So observe that there are actually 5 cases here, only written together. Some of them are written together since they apply the same function. You can translate the system into this map into this system, whose termination is, again, equivalent to the convergence of this. And this one, it turns out that we can prove the termination of automatically. Now, if you were using the unary representation, we could still adapt it to represent a system to simulate this function. But there is no hope proving the termination of that one because we can't even do it for way simpler maps that are known to be convergent. So this is like the first non-trivial test that the system we have passes. And here's the proof. So these are just matrices that are spit out by our prover that under the hood uses some SAT solver to satisfy a formula. And it solves a formula with a few hundreds of thousands clauses. Not that the size of the formula is really indicative of its difficulty, but that's the order of the magnitude of the formulas that result from this approach. And here I have some empty entries. Although I haven't mentioned it, the matrix interpretation is actually a simpler version of what we are doing in reality. So there's a variant of it where you extend the integers with -infinity and change into what is called the Arctic semiring of integers. And then that gives you another way to prove interpretation, which is in some cases more powerful than the matrix interpretations. So this is such a proof. So the empty entries are minus infinities, and one can check again with an appropriate order that all of the rules are decreasing under this interpretation. So this witnesses the termination of Farkas map, and since it's for the Farkas system, and since it's equivalent to the convergence of this map, this proves the same result that Farkas had, only fully automatically. So another partial problem that we look at is leaving out a rule from the original system. So this is the original system that simulates Collatz. So leaving out a rule from the system can only make the problem easier, or at least it cannot make the problem harder. So this gives us like an idea of where we are in terms of, the capabilities of the systems in handling a system like this. Because if we are unable to solve even the, slightly easier problems, then there's no hope of solving the original one via such an approach. But this this test we can actually pass. All 11 subproblems turn out to be solvable automatically. Some are almost trivial. For instance, if you remove this rule, then you're just encoding the map that divides a number by 2. And termination of that with this encoding is trivial to see, even for automated methods. So there is another sense in which this serves as a partial solution, which I haven't completely described, but I'll still mention again, just to give you an idea. So in reality, termination proofs are not done in a single step. You remove rules from the system in a sequence of steps in such a way that the smaller system's termination implies the termination of the full system. So this is a technique called relative termination. So having solved all 11 subproblems means that the ability to remove any single rule from this system via relative termination settles the Collatz conjecture. So it in some way solves the rest of the problem, the easy part of the problem, and the hard part becomes just finding an interpretation to remove a single rule. And relative termination works by ordering some of the rules non-strictly, some of the rules strictly. The strict rules you can delete. And then the proof obligation becomes to show the termination of the remaining rules. So this is yet another partial problem that we looked at. So you can consider the Collatz trajectories modulo some number. So this comes up mostly in the probabilistic study of the Collatz trajectories. But the specific problem that we are looking at is it the case that all residue classes mod 8 are reached eventually in some trajectory? So this graph shows how the transitions occur. And the way to read it is if we have some number that is mod 3, so there's 3 mod 8, then applying the Collatz rule brings it to a number that is 2 mod 8. If you have a number that is 2 mod 8, then applying the Collatz rule may either bring it to a number that is 1 mod 8 or 5 mod 8. So for these transitions, we were able to prove automatically that if there is a non-convergent trajectory, then it cannot avoid reaching 2, 3, 4, and 6 on this graph. But the remaining cases are whether 1, 5, and 7 has to be encountered in all trajectories. But we were unable to solve these. And these serve as still weakened variants of the Collatz conjecture to tackle using these approaches. So next, I'll show you some more problems that you can attack using this formalism that are seemingly different than the Collatz conjecture, but it turns out that you can reformulate them in such a way that they are equivalent to the termination of some smallish rewriting system. So here's one problem. So Kurt Mahler asked the following. Is there some positive real number psi such that the fractional parts of psi multiplied by 3/2 raised to the power k is strictly less than 1/2 for all k? Turns out that this relates to some problems in analytic number theory, and this question has been open for a long while. And I won't really describe it, but I just want to show you that you can answer this question negatively by showing that this system is terminating. And we have more details about how this exactly goes in the paper. There's another problem that you can handle in a similar manner. So this can be seen as like a toy version of Collatz. So Erdős asked, when does the ternary expansion of 2 to the n omit the digit 2? So this happens for n up to 8. So Erdős conjectured that it doesn't happen for n greater than 9. But again, this kind of simple looking problem is also open. And you can adapt the system that we have to compute the ternary expansions of the numbers by inverting the rules. So what we had can be seen as computing the binary expansions of mixed base numbers by pushing binary symbols to the right. So instead you make it so that it pushes ternary symbols to the right. And then you delete the ternary symbols that are 0 or 1, but you don't delete, you keep 2. And then if you are able to reach this representation, it means that you've deleted all the zeros and the ones. And it also means that there was no 2 in the string. So then you can keep rewriting indefinitely. So in this way, termination of this system for certain starting strings that are encoding the powers of 2 becomes gives a way to answer this question. But neither of these are again solvable, or at least we weren't able to solve it using the methods that we have. And to conclude, so some open problems. So we've focused mostly in our experiments on matrix interpretations because they've been the technique that's been the most powerful in resolving termination problems that have withstood other techniques. But it is still worth studying the efficacy of techniques other than matrix interpretations, or rather, developing some new techniques that subsume or are strictly more powerful than matrix interpretations. It is also of interest to prove the non-existence of matrix interpretations for any dimension for the system that we have, which might be possible. It is possible for some concrete rewriting systems. So another thing that we can do is to move from string to term rewriting. So term rewriting is more expressive, and you can represent many kinds of computation more compactly using term instead of string rewriting. And the techniques that I've mentioned all translate to term rewriting as well. So one question is, does there exist an even better encoding of the Collatz conjecture in terms of term rewriting termination that you can approach via the same methods? And another thing that we are unable to do, but would very much like to do so, is to inject specific knowledge about the problem. So there are a lot of results that are known about Collatz that could simplify the problem, but we are unable to encode any of them or inject any of them into the rewriting system or our termination proofs, because it's kind of an inflexible formalism for searching for proofs. So this is yet another thing that is of interest. And that's it. So thank you for listening. If you have any questions, I can take them.
Thank you, Emre, for a great talk. Questions, please. All right, I'll start with some questions. You know about the recent proof by Terry Tao that showed that there are infinitely many sequences of numbers where there are no counterexamples to the Collatz conjecture. Are you aware of this work?
That, as far as I know, that only shows that you can bound the lengths of the trajectories, or you can show that each number reaches a number, another number, or not each number, but almost all numbers under the natural density or the integers reaches a number that is not strictly less than the original starting number, which would allow you to conclude prove the Collatz conjecture, but like a logarithmically bounded number. So sorry, I couldn't restate it exactly, but it doesn't really translate because it's a statement over not all initial numbers for which all of the systems and the formalisms that we are considering are working over the worst case, not the average case, and that's an average case of a kind of result that Tao proved.
Okay.
So you would need to be able to show that for every starting string, you reach the Collatz trajectory reaches a strictly smaller number.
I had one more question. So instead of trying string rewriting systems, what do you have any thoughts about encoding this as a termination of a Turing machine or some other kind of machine? Recall that there is a paper by Scott Aronson and Adam Yedidia where they showed similar connections between, say, the Riemann hypothesis and they show the existence of a machine. If only you could show the termination of that machine, that would correspond to, if I recall correctly, a counterexample or something like that. I don't exactly recall the connection, but it has some similar flavor to what you are doing as well, right? So I was wondering, what about that approach? Have you thought about it?
Yeah, for Collatz, it's unclear whether you can do it. So because termination is a pi2 kind of statement, so it's a for all exists kind of statement.
Right.
So in order to be able to encode it as the termination of a Turing machine or the halting of a Turing machine, we would need to be able to place, so we would need to be able to find a sentence, a sigma 1 or pi 1 sentence that is equivalent to the statement of the Collatz conjecture. And there are many problems in mathematics where it's unclear whether that is possible. So Collatz is one of them. So the best upper bound that we have is pi2.
Albert at Sirius has a question. What kind of...
Sorry, yes?
I'm going to read the question out for you. What kind of solvers do you use to find the solutions? Is it propositional, SAT or SMT, CDCL, local search, etc.?
So we use propositional SAT. We use a CDCL SAT solver. Ideally, you would be doing this using an SMT solver because the constraints that we have are expressible in quantifier NIA, quantifier-free NIA, so nonlinear integer arithmetic. But many people in the termination community also found out that handcrafting their own encodings was almost always more effective than just using SMT solvers. In fact, so for this work, we have implemented our own solver that does a translation to SAT. And even for the problems for which we know there is an interpretation, so for instance, this interpretation, it is easily found by other termination tools that translate into SAT, but it's not found even for the correct choice of parameters. Like we know the dimension at which the interpretation exists. So even if we make all the correct choices, for instance, a solver that uses SMT actually fails to find it in time much longer than it takes to find one with SAT. So local search, one might try, and we did, although it's not really particularly effective. And there are, like in the paper, there are some more discussions regarding the SAT solving aspect of this. So there are some observations that we had, although I didn't have time to get into them now. But in the end, encoding into SAT by unary bit blasting and solving via CDCL appears to work best, at least among the things that we tried.
I'm assuming the code, etc., is available on GitHub or somewhere.
It will be along with, so once the conference version is available and the full version is put on archive, they will have, I mean, the code is not the interesting part of this generally, because like most of these results, you can achieve them with a few other termination tools as well.
Mm-hmm.
Yeah.
Any additional questions?
I was just wondering how big the numbers are in your matrices you're considering.
That's a good question. So one thing that I haven't mentioned and nobody asked was that while doing the search, you actually need to fix a bounded domain where these coefficients are coming from in order to get a finite formula. So as you can see, for instance, here in the interpretations, the largest occurring value is 4. But in the set encoding, you need to mention the variables that would occur in the interpretations of the rules as well. So for this specific example, 8 is the largest number that occurs. And we bit blast using a unary encoding. And since it's more propagation friendly compared to using a logarithmic encoding. And for instance, I don't have it in the paper, in the slides, but for one of these systems, there is an interpretation that uses values up to 30 that occur in the interpretation, although, and we are only able to find it because it's so low dimensional. It uses just 2-dimensional matrices where the largest occurring value anywhere in the interpretations is 30. So that results in a feasible formula to solve.
Okay, thank you.
Final question, do you have any hope of solving the Collatz conjecture with this method?
Probably not, but it's very addicting to try.
Yeah.
Well, the thing about these is you can, like the one particular thing about the choice of matrix interpretations is you can scale them. And they're known to have a proper hierarchy of problems that are solvable via a given dimension. So one can hope that increasing the dimension can, after a long search, lead to an interpretation. But as I said, it may also be the case that no interpretation exists. There are like concrete examples of rewriting systems for which there is provably no matrix interpretation. Because the existence of a matrix interpretation actually places some constraints on the longest derivations in the system in the rewriting system that you can have. And so systems that have too long derivations do not admit matrix interpretation proofs, although they are provable by other methods.
Any additional questions? If not, let's thank Emre for a fantastic talk. Thank you, Emre. All right, so with that, we close this session, and I believe that at 2 p.m., is there a gather town? I don't know. Umaid, is there a gather town at 2 p.m.? Or
I believe you're free to join Gather Town.
at 11 a.m. PST, PPT, right? All right, thank you, everybody. Bye-bye.
Thank you. Bye-bye.
Thanks.